Okay, welcome everyone. So if you remember in previous lecture what we say that in order to tune the properties of the material, we have to understand the structure and being able to tune the structure of the material. So if we can change the structure, we can change the properties of material. So we can let the material attain certain properties if we are able to change the structure of that material. And in order to talk about the structure, we have to start with the basic element of any structure. Okay, that's why in this chapter we'll be start talking about the atomic structure, and then we're gonna build upon that knowledge to go further and to discuss more deeper, and we're gonna cover different topics that's related to the structure of the material. Okay, so in the beginning, we're going to look at the atom, a single atom. Okay, we're going to give a closer look, and then we're going to move to say what's going to happen if two atoms see each other. And then we're going to say what's going to happen if millions of atoms see each other, how they talk to each other, how they correlate to each other. Okay, great. Now, why this is important? Because we know that the interatomic bonding at the end is something very important and determine the properties of the materials. We know that the example of carbon, you get the graphite, you get the diamond. In the graphite, all the graphite and diamond, they have the same elements, which is made of carbon, but still they have different properties. So graphite, greasy and weak. The diamond is one of the hardest materials that we know in the nature. Great. So this is why it's very important to understand, why certain material has certain property. So we need to understand the interatomic bonding between the atoms. Great. So as you know that the atom. So this is also going to be in a brief discussion, because we really we are under the assumption that you really took the enough background about this in Chemistry 101, and also in any other general chemistry course. This is just a quick revision, something that we will use in order to build on in our subsequent discussion. Okay, great. So in the atom side, the atom, we know that we have protons, we have electrons, we have neutrons, and also we know that protons, electrons are the ones that have charges. So protons positive, electrons negative, and then the mass of the atoms will be determined by the proton and the neutron, as both of these two have heavier masses compared with the electrons. Okay. Now, just for your knowledge, AMU could be something new for you. AMU is atomic mass unit. It's just a reference scientists agreed to use. They use mass of carbon as accepted reference atom, because carbon-12 has 6 protons, 6 neutrons. So they say carbon-12 has 12 AMU. And if you want to measure the masses of any other atom, we're going to use it in a reference to the carbon-12. So 1 AMU equals 1/12 mass of carbon. For example, for helium-4, what's going to happen? 4 times 1/12. That's going to give you the mass of the helium in AMU. Great. So the mass of atoms depends on the protons and neutrons. Electron has negligible contribution toward the mass of the atom. Okay, great. So that means 1 AMU. That means you have 1 proton and equals 1 proton equals 1 neutron. Okay. Mass number. So is mass number of atom. Okay, gonna be the result of the summation of the number of protons that exist in the atoms plus number of neutrons. Right? And in carbon case. So in carbon, if you have 6 protons plus 6 neutrons for C12, end up having the mass number, the mass of that atom. Okay. The atomic number is also the number that will be used to classify different atoms, and that depends on the number of protons inside the material, inside the atom. طيب. So we can say atomic number 6 because for the carbon, because the carbon has 6 protons. Now all the carbons have the same number of protons. Okay. What about the so what about the neutrons? Well, the neutrons could be equal to the protons. So we have equal weight. So for example, in C12 we have 6 protons, 6 neutrons. Okay. However, in nature, you can find different types of carbon. They have the same number of protons, but they might differ in number of the neutrons. As you can see an example over here. So C11, 6, that means we have the mass of the carbon, of this type of carbon, as 6 protons plus the remaining is the neutrons, right? So we have 6 protons, 5 neutrons. Here we have 6 protons and 6 neutrons. 6 protons and 7 neutrons, okay? So, I mean, the same element might have different masses, and that differences between them arises from the fact that they have different neutrons. And we call this kind of atoms isotopes. So that means carbon have different isotopes, and each isotope has different number of neutrons. Right. By the way, the atomic number equals the number of protons and the number of electrons. This only in the case you have a neutral atom, right? So atom that has number of protons equals the number of electrons. If you pull an electron from that atom become an ion, right? So that means at that case, the number of protons will not equal to the number of electrons, okay? Just for your information. Okay, great. So for the isotopes here, for the isotopes when they have different number of neutrons, how we can calculate then the mass? Because they have different neutrons. In order to do so, we're gonna say the average atomic weight equals to the summation of fraction of occurrence of that isotope times the atomic weight. Okay? For example, this kind of isotope, what is the fraction of occurrence of the occurrence of such isotope in the nature? Right? And then let's say 10%, 5%, we're gonna multiply 5% times the mass of this atom. And then what is the fraction of occurrence of this atom? Let's say 50%, 60%. We're gonna say 60% times the mass of this, okay? And then we're gonna do the summation that's gonna give us the average atomic weight of an element. If you take an example, we're gonna take an example in a while, okay? Okay, so we have atomic mass, which is representing the mass of atoms that depends on the proton and neutron. And then you have atomic weight, the average weighting, which means that we take all the atomic masses, different isotopes, and then you take the average by doing the summation, the equation that I just showed you in the previous slide. In order to express the atomic weight, there are 2 units. Either use the mass per mole, gram per mole. I guess most of you are familiar with this, gram per mole, where 1 mole has 6.022 times 10 to the power 23 molecules or atoms. Okay. The other way to express that we say AMU per atom. So, for your knowledge, 1 AMU per atom equals to 1 gram per mole. Okay. So we're going to use, I guess, in this, and we'll use this in an alternative way. But most of the time, we'll be using 1 gram per mole. Okay, if you want to take a quick example here, for example, chromium has 4 neutrally occurring isotopes. This is the occurrence of this isotope, 50, and we know that 50 is representing the number of protons plus the neutrons, okay? 50. Now, that's chromium 50 has a certain atomic mass, and then chromium 52, the occurrence, this is the occurrence, and this is the atomic mass. And in order for us to calculate the average atomic weight of chromium, what we will do, we'll multiply the fraction of occurrence times the atomic weight of each isotope, and we do the summation of that in order to come up with the atomic weight, what's called the average atomic weight of the chromium. Okay, so this just gives us an idea of how we can calculate the masses of the atoms. Okay, or the elements. Okay, great. Then we move to the second step. Okay, can we what else is important to know about the atom, right? And I guess one of the important elements of any atom is electrons. We need to know more about electrons, right? Where the electrons are they, and we know that they have negligible masses. Whether they have, we need to know whether they have also negligible contribution to anything. Well, it turns out electrons play a major role in determining the type of interatomic bonding between the atoms. Okay, so we need to know more about those electrons. We need to know more characteristics about those electrons. Okay, so there are different models through the history trying to describe the electrons and where they exist and how they correlated to the nucleus, right? One of those models, Bohr's atomic model, where he said that, look, in the atom, in the middle, you have what's called the nucleus. And inside the nucleus, you have positive charges, positive charges, which is coming from the proton, and neutrons that has neutral charges. So the nucleus has positive charge. And then around the nucleus, you have the electrons revolving, not in a random way. So what Bohr is trying to say, look, electrons are revolving, yes, but not revolving in a random way. Rather, they are revolving in a specific orbitals. Specific orbitals that mean each orbital has a certain energy. So electron revolving in this orbital has specific energy and specific position, right? For that electron to move to another orbital, that electron has to gain energy. For that electron to get back to the original energy, it has to, original orbital, it has to lose energy. So Bohr model is trying to say that, look, that discrete orbitals and electrons have quantized, and their energy are quantized. I mean, they have specific amount of energy. Okay, and the energy of an electron depends on the size of the orbits. So the energy is lower for smaller orbital. The energy is higher for larger orbitals. Okay, so and between those orbitals there is no electrons. There are no electrons. Electrons cannot exist. There are no orbitals between those orbitals. Okay, it's like when you're going down the stairs. Okay, there is no stair in the middle, right? So one step, and then you go to the other one. Right, one step to the other step. So there is no energy level exists between the steps. Okay, great. That was great. So Bohr was able to come up with something more solid, which really helped a lot in developing other models, other future models. Okay, so we have nucleus in the middle, and then we have electrons revolving. Electrons have specific energy. The problem is when they try to generalize this model to more complicated atoms. Now, when you apply this to hydrogen, things are very easy because hydrogen has a single electron. When you go to more complicated atoms with more electrons, it turns out Bohr model cannot really explain everything. Okay, so there is some limitation when we use the Bohr's model. This is why other models came to fill that gap and try to explain and correlate between the electron and nucleus, even when we're dealing with atoms that has atomic number, let's say 92. Okay, or other atoms other than the hydrogen. Okay, so the other one is called wave mechanical model. Now, for wave mechanical model, what's happened is Schrödinger in 1962, he took the Bohr model and then he tried to modify it. He tried to build on that knowledge to come up with something that is more can be generalized to all the atoms. Okay, so what is really different between wave mechanical model and the other model is that the wave mechanical model is telling you, look, we have to deal with electrons not as a particle. We have to deal with electron as something that has a nature-like, has a wave-like and particle-like. Okay, so when you say wave-like, that means you cannot define the exact path of an electron. Okay, we can only say the probability of finding electron at that position. We cannot identify the position of that electron. Okay, and then they say we can, we can plot the probability of finding electron around a nucleus. Okay, and as you see, the probability of finding electrons represented by the blue color. As you get closer to the nucleus, the electrons, there is high probability of finding electrons around the nucleus. If you go further away, there is less probability that it's less probable that you find electrons far away from the nucleus. Okay, great. So they call this the electron cloud. The electron cloud. Okay, so so this is an electron cloud for 1s, for 2s, for 3s. Okay. Between these, as you notice that between them, you see the white color. That means electron cannot exist there. Okay, so the probability dividing them 0, right? And now then they say this 2D plot can be extended into 3D plot. When you extend it, you're gonna get this, from this, you're gonna get a sphere, right? So now you get a spherical representation of the probability of finding an electron around the nucleus. Okay, great. So quick comparison between the wave mechanical and the Bohr. Bohr is telling you you're going to find the electron at a specific point around the nucleus. However, the wave mechanical is telling you we're going to find the probability of finding electron is higher at a certain position compared with other positions. Okay. And also the other difference between wave mechanical model and Bohr model is that the Bohr model is telling you that there are some levels, right? Some orbitals where the electron can sit, right? But by the way, let's give more explanation. Let me walk you through this plot over here. So y-axis have the energy 0. That means the electron is very far away from the nucleus. Nucleus has a positive charge, so that means nucleus positive charge is trying to pull the electron toward the nucleus, right? So there's something that's pulling it, so the electron cannot get away. Now, if the electron is really far away from the nucleus, that force will be lower, right? So that means if the electron is very far away, we can call it a free electron, right? So 0, that means electrons are free. If as you get closer to the nucleus, there are certain energy levels, right? Energy levels where the electron can sit. Now, the wave mechanical is saying, okay, Bohr, you did a wonderful job in determining that there is specific energy level, but I would like to mention that, well, those levels also can be divided into sub-states or sub-energy states. For example, the 2 can be divided into 2 states that are very close to each other, right? And this is also the main difference between the two models. Okay, great. Now, the question, can we come up with something that can easily identify characteristics about the electron? The answer is yes. How is that? Well, when you go to buy an item from the market, right, there's a barcode. You scan the barcode, it's going to give you information about that item, right? We want to, for electrons, there are 4 quantum numbers that we're going to use in order to identify electrons, right? So those 4 quantum numbers, the principal, right? Something about the orbitals, So the principle is telling you about the size of electron's orbital. How far the electrons from the nucleus, okay? So it's the energy level. So the N is about, it's called principal number, it's about energy level. And then L is the orbitals within that energy level, and it's telling you about the orbital shape. For example, here for S, we have a spherical shape. For P, you can have different shape, right? Have a nodal surface with dumbbell shape. And then this is for P. For D, you have other shapes. You get more in complicated shapes. So L is telling you something about the shape of the orbital when you plot it in 3D, how it looks like. Okay. Magnetic. Okay. A magnetic is telling you now for P. Okay. P. How many energy states you have within P? Right. Do you have one state, or two states, or three states? Okay. So number of energy states for each subshell. For example, let me tell you something. For example, for P, always we have Px, Py, Pz. For S, we have only one level. So S has only one state. That means two electrons can sit there. For P, well, we have three states, right? That means you can fill 6 electrons. Each state gonna take two electrons, okay? The spin moment is telling you for that state, you're gonna have 2 electrons, but they cannot have a spin moment, the same spin moment. One has to be up, one has to be down, plus one of the half, the other one minus half. It's called spin orientation, okay? Just, you know, if you want to bring everything back to the together, if you look at this table, for example, when n equals 2, what are the possible value of L? Well, we come to this here. The possible value is n minus 1. That means 2 and then 0 and 1, right? So we have 2 minus 1. That means we have 0 and 1. Okay, 0 and 1. Now for 0, the value of ML is equals to minus L2 plus L, right? So that means you have 0 at that. So there is only one subshell with one orbital, okay? One orbital. And that orbital will accommodate maximum of 2 electrons. Now if you go to 1 here, 1, so minus 1, 0 plus 1. Why? Because 1, value of ML equals to minus L2 plus N. So minus 1, 0 plus 1. 2p has three orbitals. Minus 1, 0 plus 1 is called px, py, pz. Px, py, pz. So they have 3 states. So 3 states, each state can accommodate 2 electrons, so the total of 6 electrons. Okay, great. Similarly, now if you notice that the value of n can go from 1, okay? Can take integer number, it can go from 1, okay? Sometimes they refer 1, 2, 3, 4 to 1k, L, M, N, O. Okay, great. So that's going to help us to identify each electron, where it says, you know, what is the energy of that electron, where is how we can plot the probability of finding that electron in the atom. Okay, great. Now, if the number of the electrons, if the number of principal quantum number n increase, the energy increase of that state, of that orbital. For example, 1s has lower energy than 2. 2s has lower energy than 3s, okay? Now, also within the energy level, within the same quantum number 2s, as the L value increase from 0 to 1, because S 0, P is 1, okay? Notice that the energy also increases. Sometimes there is an overlap. Notice here that this is 3S, 3P, 3D, 4S, 4P, 4D, 4F. But you notice that 4S has lower energy level than the 3D, right? So what we need to do, the electrons first, always electron first will fill the lowest energy states, and then it's going to fill the large energy state, okay? The states with higher energy, okay? Okay, let's look here. Let's take an example here. Let's take this example. Okay. First, we have n equals 1. We have 1s. Okay. N equals 2. When we say that the L is limited by value of n, معناته we have L equals to n minus 1. That means we have 0, 0, which is representing the s. 1 is represented by the p. We said the s has ml value, 1 ml value, right? So we have one state, one orbital. 2p has 3 orbitals with a px, py, pz, which is minus 1 plus 0 and plus 1. Okay. Now, and then we have the 3 and the 4. Okay. The electrons first going to go and fill the lowest possible state of energy. Okay. Let's do this here. Okay. Okay. Let's do this. So it's gonna go and fill the first state. Oh, okay. Let me get here back. Okay. We're gonna go to that example in the next slide. Now, the other thing we want to talk about, after the electron gonna fill the lowest possible state of energy, then what's gonna happen? We're gonna lift with electrons at the outermost shell. Right? What's called, those electrons are called valence electrons. Those electrons are very important. And if those shells are not filled, what's going to happen? If they are partially filled, that means those electrons are not stable. So they want to lower their energy by getting into a reaction, getting into a certain war. You know, they would like to fight in order to either to get rid of their electron or they to accept the electron in order to reach to the stability. Right? So the valence electrons are very important, concept, because that's going to help in determining the type of interatomic bonding that might exist. Okay, and if you look here, all the one with the blue color over here, light blue. I don't know why you call this not a color anyhow. Those representing the valence electron. Now notice for the stable ones, here S2, so S orbital is filled. P6 is filled, okay, great. So that means we have 8, so they are stable. This is why they're called inert gases, so they're not willing to get into any reaction, they're stable, okay? However, other atoms, other elements, they're willing to get into reaction because here you have 2 plus 1, 3, 2 plus 2, 4, and you have 8. Those orbitals can get up to 8 electrons, so they are partially filled. Okay, so that's called valence electron. So now any atom would like to get into any reaction in order to assume the configuration of those stables 1. Okay, let's take an example here. Okay, so we get the iron. Iron has atomic number 26, right? And when you do this electronic configuration, 1s2, 2s2, 2p6, 3s2, and then 3d6, 4s2. Notice that first we filled the 4s2 because it has lower energy state than 3d, and then we went to 3d to fill the 3d, right? Now notice that we have those orbitals are not filled yet, so we have to fill them. They're partially filled, right? So what we need to do, so this is considered to be the valence electron. So 2 plus 6 here, you have 8. And remember that the d orbitals can accommodate up to 10 electrons, up to 10 electrons. So now you have here still you have 4 electrons that are missing, right? 4 electrons that are missing. Okay, great. Notice now in each state, as I mentioned earlier, there's spin up, spin down. Okay, spin up, spin down. According to Pauli's exclusion, that each electron state hold no more than 2 electrons spinning in the same direction. It has to be spinning in the opposite direction. Clear? Okay, great. What's going to happen if we take one of those electrons? Now the atom become an ion. For example, if E plus 3, what's going to happen? 3 plus. What's going to happen? Well, we are losing some electrons, right? So if we're listening to some electron, so 3 electrons, we're going to take these 2 electrons plus 1 here. That means we end up having 3D 5. Okay, great. So that was a quick revision for the, the subatomic structure, how we can calculate the masses, and then electronic configuration. For sure, there are many details that related to this topic, but it's beyond the scope of this course. Hopefully, that was kind of a refresher, a good quick revision for that topic. Now we're going to go to the periodic table. Now, if you look at the periodic table, don't think that all these elements are randomly positioned in this table. No, they are classified in a certain way. Now, if you look closely, before I explain this, if you look closely here, this is the periodic table, right? Each row, okay, is representing a higher energy principal quantum number. So N1, N2, N3, N4, N5, N6, N7. Okay. In the same time, all the column, we call it groups, all the groups have the same number of valence electrons. So they have the same number of the valence electron. Now, some of those, they share some properties, and some of them, sometimes there are some changes. For example, some of these elements might, in the same column, they have the same properties, but this is not a general rule, okay? So there's some, there are exceptions here and there. But if you look closer in this table, what you notice that most of the elements are metal, right? Most of them are metal. And if you go to the far left, you're going to find what's called the non-metal. Now, all the metals, they have similar characteristics. They are electric conductive. They are kind of durable. They have more elasticity in terms of the mechanical property, right? No, they vary, but they have kind of more flexible looking shape and material made from such atoms or elements. However, here, if you go to the non-metals, mostly they are more brittle, okay? Usually exist in a liquid form or gaseous form. They can exist in a solid form, but most probably in a brittle manner. It's more like brittle. They're not flexible, right? Like the other. Also, if you look here in the middle, it's called the one here in the middle, starting from this group up to this group, is called the transition metal, right? Where the d orbitals are partially filled. Okay, so the orbitals partially filled. So it's called transition metal. Okay, what else? So the atomic number increases, go down. The other important concept here is that what's called the electronegativity. Now notice that the inner gas, those gases are stable. So they don't want to get into any reaction. Then we call it noble gas or inner gases, right? They are stable because the outermost shells are filled, right? So there's no reason for them to get into any reaction, okay? So they have a peace of mind, sitting and relaxing. However, all the other elements here at the table, they have this issue of they're trying to assume this kind of configuration where we have filled subshell, filled outermost shell, okay? Now, if you look at the hydrogen, if you look at the helium, it has 2 electrons, and this helium has one s. I mean, one orbital. That orbital s, we say that has only one state of energy. That means that can accommodate 2 electrons, and already it's filled. Okay. Now, if you add one additional electron, they're going to have lithium, right? Lithium is a very important element, Look at your iPhone, right? Lithium-ion battery, right? So lithium has atomic number 3. It has 3 electrons. Now, 3 electrons, that means it has one additional atom, one additional electron. So the lithium is willing to get rid of that electron in order to assume the configuration of the electronic configuration of the helium, right? So, and if you go to the far right here for fluorine, fluorine is missing one electron in order to get the configuration, right, of the neon over here, right, for 10. So this is why the fluorine will do its best in order to acquire that, or to accept an electron in order to have the electronic configuration of the neon over here. Okay, great. That means there's something called electronegativity, electropositivity, right? So electronegativity is increasing as you go from left to right, from left to right. What does electronegativity mean? That means as you go from left to right, the atom is willing to accept electrons. Their tendency to accept electrons is higher, right? So this is why here has higher electronegativity compared with here, right? The elements that are sitting here. So those atoms has higher tendency to accept electrons in order to acquire the electronic configuration of the inert gases. Okay, electropositivity is the opposite. As you go from right to left, well, atoms willing to the tendency of giving up electron is higher, right? So lithium is willing to give electron whenever it's possible in order to assume the configuration of the helium, right? So the electropositivity increase from right to left. Okay, great. So this is just a general view about about the periodic table. We can also identify the electronegativity value for each element. So as you can see here, as you go from left to right, the electronegativity increasing from lithium up to fluorine, right? So electronegativity is increasing. So, right, and not here. There is no value because they are not willing to accept any electrons, those inert gases. Okay, great. And this is very important because when you talk about bonding between atoms, the electronegativity differences will determine we're going to talk about this, the type of bonding that can exist between the elements. Okay, great. So we call the group over here alkali metal, right? And then this transition metals, this non-metal, other metal, halogen, and then inert elements, rare earth elements. It's just a quick revision of what's called the periodic table. Okay, wonderful. I hope by now at least you have some basic that can help us to move further in this course. Inshallah, next class we're going to talk about the atomic bonding. Okay, great. Thank you so much. See you in the next lecture. Thank you so much.